In this video, we are going to look into what is discrete time periodicity, how it is different from the continuous time periodic signals, and some examples therein. Also, if we add two discrete time periodic signals, what is the way to determine if the resultant signal would be a periodic signal or not. Periodicity of discrete time signals. So for discrete time signals, when we discuss about periodicity, it is rather a little bit more involved as compared to the continuous time signals. Let us first visualize what does periodicity means in discrete time signals. So say we have function x of n. So if this function is equivalent to x of n plus capital N, right? So that is, we have an integer time period n such that x of n plus time shift by capital N, right? So if it doesn't affect the overall signal, the signal remains the same, so this means the signal is periodic, right? The condition is that n should belong to positive integers, right? Let us look into one simple example and try to understand this further. So say we have a signal x of n, that is a generic signal a cos let us say omega n plus some phase shift pi, right? And we want to check its periodicity. We can say a cos omega n plus pi. This is equivalent to, from here we can say a cos omega n plus n, right? So we would have capital omega n plus from here this pi phase shift, right? So this omega n is a new term that we have obtained, and for that, for this signal to be periodic, we can say that it would be periodic by multiples of 2 pi, and then we have a k that identifies the multiplicity in integers, right? So where this thing and this thing can be equated, right? So this means that our omega n is equal to 2 pi k, or simply n is equal to 2 pi by omega k. This is our important expression. So what we need is, we need the value of k in such a way that n becomes an integer. So that was our original condition over here. So for k belonging to any integer value such that n becomes positive integer, so if this condition is met, this means that the signal is periodic, and if this is not met, this would mean that the signal is not periodic. Furthermore, the smallest value of k for which this n would become integer, so that is called the fundamental period or fundamental integer period, right? So based on that k, we can find the fundamental period that we call as n naught. So the smallest value of k which will make this expression an integer value, that would be a fundamental period. Let us see one example and look into this further. So in the first example, our x of n is equal to 3 cos 4n plus pi by 4, and we need to find whether this is a periodic signal, and if it is a periodic signal, what would be its fundamental period, right? Over here I have written the expression that we have found earlier, that is n is equal to 2 pi by omega times k, right? So over here this omega is simply, that is 2 pi f times, in continuous time it was t, now we have an n, so this is our omega. So this means that n is equal to 2 pi by 4 times k. So we can notice that for any value of k, when k is an integer, we cannot find an n that would be an integer. That is, if you set k equal to 4, so this will become 2 pi, which is not an integer value, right? So for any k which belongs to an integer value, we cannot find n such that it belongs to an integer value, right? So if this is the case, this means that x of n is not periodic. Let us take one more example. So in this example, we have just added 1 pi over here. So now our omega is equal to 4 pi. So this would mean that n is equal to 2 pi by omega, that is 4 pi into k, right? And this would mean that this pi would cancel with this pi, and if k is equal to 4, we would have n naught, that is n naught would be equal to 2 in that case. That is our fundamental integer period n naught is equal to 2. But do note that k could have higher values, higher integer values, and that would also make n an integer. But that integer or that integer period would not be the smallest one, and it would be actually bigger one. So what this means is that this signal is periodic with n naught equal to 2. So from these two examples, we can conclude that periodicity depends on the value of omega, and we can say that if omega is rational multiple of pi, so this would mean that the signal is periodic. So for example, we can have omega that is equivalent to, say, x by y times pi, right? So if x and y are integer values and they multiply with pi, so that particular sinusoid would be a periodic signal. Otherwise it's not a periodic signal. Or simply, if you don't find a pi in discrete time signal, so this means that the signal is not periodic. So in this example, again, we have a very simple sinusoidal function, that is cos pi by 2n, right? And we are interested in analyzing this signal further, right? So let us say this is our omega. So our fundamental time period or integer period would be 2 pi by omega, that is pi by 2 and multiplied by k. So this would be equivalent to 4k, and this would indicate that our n naught 4 is already an integer, so if you multiply by 1, it will become 4. So it is 4 for k equal to 1, right? So what does this k equal to 1 mean? This is actually our envelope, right? And these are our values, discrete values that would be there in the sinusoid. So let us understand this by means of one plot. Just for guidance purpose, I would make a cos function in continuous time. So n not equal to 4 means that we would have for one cycle 4 values. The first value could be over here. This could be our second value. This would be our third value, and this would be our fourth value, right? So 1, 2, 3, 4. In this envelope, this is our envelope, that is k equal to 1. So this one envelope contains 4 discrete values of n naught, right? So these 4 values are appearing over here, but this envelope would be repeated at other intervals as well and on the other side. So k determines the envelope, and n naught is the number of values given in that particular interval. A very important point herein is that by increasing the frequency or omega of a discrete time signal does not necessarily mean that you're going to increase the oscillations. The oscillations are going to increase up to a certain point and then they will come back. That is, increasing omega increases oscillation up to a limit, and then the oscillation decreases. Then it would all again increase, and then again it would decrease. This concept can be better understood with the help of one graphical illustration. Say we have a function x of n, and that is equivalent to cos omega n, right? So omega can have different values. Let us increase the value. Say initially our omega is equal to 0. So if omega is equal to 0, so this means that cos of 0 n. So cos of 0 is actually 1. So for all values of n, we would have x of n equal to 1 for all values of n, right? And this is depicted over here, the first plot. That is, if you put omega equal to 0, cos of 0 into n, or x of n, would have all values equivalent to 1, right? And it is not oscillating. So this was our first case. In the second case, let us increase omega to pi by 8. So if omega is pi by 8, so this would mean that from here n would be equal to 2 pi over pi by 8 and multiplied by k, and this would be equal to 16k, and that would mean that for k equal to 1, n naught would be equal to 16 for k equal to 1. So that is our fundamental integer period. So for omega is equal to pi by 8, right? So we have this plot, and this would mean that for k equal to 1, that is, we have one envelope. In that envelope we would have 16 integer values, 16 distinct values. So say we are starting from this point, so this whole thing is our envelope, right? And it would have 16 values. So this is our k equal to 1, right? And it should have 16 values. So in the third case, this omega is set to pi by 4, and you can observe that the oscillations has increased. You can again find the value of k and n naught for this plot. Furthermore, if we increase omega to pi by 2, so again the oscillation has increased. Finally, if we set in this plot, if we set omega equal to pi, so the signal will be continuously toggling up and down in the cos function, right? So this has the maximum oscillation. So for n equal to 0, it would have a plus 1 value, and when n is equal to 1, it would have a minus 1 value. So beyond this point, again if you increase omega, right, so the oscillation is not going to increase, and in fact you will get back this plot. That is, cos of pi by 2 n is equivalent to cos of 3 pi by 2 n, right? So the oscillation is decreasing, and as we continue to increase, the oscillation would decrease, and again at 2 pi we would have the same plot as the original one. So increasing up to the maximum point, then decreasing, and then if you continue on, then again you would get this plot and onwards. So this is basically a contrasting feature of discrete time signals as compared to continuous time signals, where in continuous time signals, if you increase the frequency, the oscillation is going to increase, but in discrete time signals it is only going to increase up to a limit, right? And then it will toggle back and forward. Finally, in this example, we have two signals, that is ej2 pi by 3n plus ej3 pi by 4n. So these two signals are added together. So if they are added together, we are asked to determine whether the resultant signal would be a periodic signal or not. So to answer this problem, I have adopted a 5-step procedure as I had done in the continuous time counterpart. So in the first step, that is step 1, we are going to check whether each of these signals are periodic by themselves or not. So if they are not periodic, then we might not proceed next, right? So if both of them are periodic, then we'll proceed next. So in the step 1, we check if each signal is periodic, right? And the way to check is that the omega, which is over here, this is omega 1, this is omega 2. So this omega 1 and omega 2 should be a rational multiple of pi. If they are not rational multiple of pi, so this means that the given signal is not periodic. So over here, omega 1 is 2 by 3 pi, which is written here, and similarly in the second case it is 3 by 4 pi, which is written over here. So in W1 we can observe that the numerator is an integer and similarly the denominator is an integer value. So this is basically integer by integer, the outcome would be a rational number. So hence W1 is satisfying this condition, right? Similarly, W2, which is coming from here, 3 by 4, is again a rational number and it is also satisfying this condition. So both of them are check, right? Next, in step 2, we convert W to the frequency domain. That is, we just simply divide by 2 pi and we obtain F1, which is equal to 1 by 3. And from here, if we divide by 2 pi, we will get 3 by 8. Now, next in step 3, we want to convert f1 and f2 to an integer value. That is, we are going to multiply with a specific number that is going to make f1 and f2 an integer values, right? And we can do that by multiplying both sides with 24, right? So if we multiply this with 24 and this with 24, we are going to find an integer value. F1 hat is 8 and f2 hat is 9. So these are integer values that we desire in step 3. So in step 4, for f1 hat and f2 hat, we are going to take the greatest common divisor GCD, and 8 can be divided by itself, 4, 2 and 1, and similarly 9 can be divided by 3 and 1. So the greatest common divisor is simply 1. So if we get rid of the subscript 1 or 2 and we have a composite f hat, so that is equal to 1, right? And in step 5 we are just going to invert the step 3. In step 3 we multiply by 24. So in step 5 the f would be equal to f hat by 24, right? So the frequency, the composite frequency or fundamental frequency is simply 1 over 24. So n naught is just the inversion of this, so n naught is equal to 24. So this gives us our fundamental integer period.